So today's lecture, we will be talking about the formalization of phase space in Hamilton mechanics to see how we can formalize the mathematical structure, let's say, using the mathematics that we went through in the previous lectures. And then the second hour, I will start to introduce field theory, and next time, which is the last actual lecture, I will be talking more about field theory and how Noether's theorem plugs into field theory. Okay, but so for now, I will start by discussing the formalization of phase space in Hamilton mechanics. So we discussed last time a lot about Hamilton mechanics and symmetries in Hamilton mechanics. So what I want to do now is to formalize that. The formalization of the phase space. So I want to see kind of what is the mathematical structure of phase space. So we saw that the mathematical structure of Lagrange mechanics was essentially that the Lagrangian was a function. If you have the configuration space, for a configuration space, M, the Lagrangian was a function from the tangent bundle of M to real numbers, right? Where the tangent bundle was the union of all tangent spaces of the phase of the configuration space. So the question is now, what is the Hamiltonian a function of? Now you know that the Hamiltonian generally is a function of the coordinates of phase space. So the coordinates of phase space we took as QA and the corresponding canonical momentum, right? So kind of the easy answer is it's a function of Q and P, but the question is, what are Q and P the coordinates of? So the question I want to answer is, what is the mathematical structure of the canonical momenta? PB. So in order to answer that question, let's consider a coordinate change on M. So coordinate change on the configuration space. So QA goes to some new coordinates, QA, which is we can write them as a small translation by some vector field K. So this is a coordinate change on configuration space, right? Assuming here that K here is only a function of the coordinates Q. So I can also invert this. So this means that QA is equal to QA minus epsilon Ka, right? That's just subtracting that term from both sides. So the question is, how do the canonical momenta transform under this transformation? So in order to see that, well, we need to look at the definition of the canonical momenta. So my new canonical momenta, capital PA, by definition, should be equal to the derivative of the Lagrangian with respect to dqa, the capital QA dot. Okay, but I can use here the chain rule of derivatives. So I know that the Lagrangian is a function of the derivatives of the q's and the q's themselves. So I can use the chain rule to write this as dl dq dot b with a lowercase q, then dq dot b dq dot a, right? Plus the Lagrangian also depends on the q's themselves. So dl dqb dqb dqa, right? So this is just the chain rule of derivatives. Okay, but I know here that the coordinate transformation here, the q's depend only on the q's themselves. Right? It does not depend on the derivatives of q's. So it's a transformation on the configuration space only. So that means that this partial derivative is equal to 0. Oops. Well, I could erase it, but it's more instructive to actually put it to 0. So that term is going to disappear. But let me also here write something for this derivative. So dq dot b dq dot a. Well, we know here. Let me actually erase that. Let me start from here. If I take the time derivative of that expression, what I find is q dot a is equal to q dot a, capital Q dot a, minus epsilon, and then let's see what I want to do. No, I want to do the following, right? It's some function generally of q. So I just want to write this as the qa the qb, because it only depends on the q's, right? Doesn't depend on the q dots, and then q dot b, right? So this means that when I do this derivative, the only way the q dot appears is here linearly, right? It doesn't appear here because the q is just a function of the q's and not the derivatives of q's. So the only place where the q dot appears is there. So I can use that to perform this derivative. So I get that dq dot b dq a, that's going to be dqa dqb, right? So essentially what you see here is called canceling the dots, essentially, because as long as you have this kind of transformation, that the q's don't depend on the derivatives but only on the q's themselves, then you can then you end up with this expression, which means that you end up with this expression where you just remove the dots on the right hand side. Okay, so this means that this capital PA, that's this derivative of the Lagrangian with respect to q dot b, but that's the lowercase pb. Actually, I wanted to use black here. Oops. So this is equal to lowercase pb, and that comes from this term. And then I have the the expression with the cancelled dots, so dqb, dqa, right? Well, this is exactly the transformation property now. If you check it out, this is the derivative of the old coordinates with respect to the new coordinates. These are exactly the transformation property of dual vectors. So that means that these canonical momenta, they are the components of dual vectors. So this means that the Hamiltonian, which is a function of the q's and the p's, is a function on the cotangent bundle. So that's T star m, and that's defined as the union over all points in the configuration space of the tangent of the dual space at each point. So just as the tangent bundle was defined as the union of tangent spaces, the cotangent bundle is defined as the union of all dual spaces. Okay, so it should be noted here that this cotangent bundle in itself, it's a if configuration space is n-dimensional, the cotangent bundle T star m is 2n-dimensional. And it's a manifold in itself. It has 2n coordinates, and we can describe them, and we can describe curves in this space as well, and so on, if m is n-dimensional. So in general, I can pick any 2n coordinates on this cotangent bundle. For example, the coordinates yr. Any 2n coordinates will do. For example, yr could be the set qa pb, but in general we can choose any coordinates on a manifold. I could introduce whatever coordinates transformations here that I want. Some will be canonical, some others will not, but I can choose any coordinates that I want. So just to take an example here, let's consider a particle moving on a circle, a vertical circle. So essentially we would have something like this. We have the circle, and we have the particle, which is free to move however it likes. So I can use here the configuration space coordinate theta. It's a one-dimensional configuration space. So this configuration space is the circle S1, whereas the canonical momentum P, that's any real number, right? Can have whatever velocity I can imagine along the circle. It can be any real number, the angular velocity here, right? So in this case, the phase space is a cylinder. It's S1 cross R. And notice that in this particular case, the phase space is a simple product between the circle and the real numbers. This is not necessarily always the case, but in this very simple case, it is. So the phase space is a cylinder here. So this means essentially that I can describe the phase space of this particle as this cylindrical structure. Let's see if I can draw that. So you have this cylindrical structure. Essentially, if I point in phase space here, well, that's a point on the circle, but it's also a momentum. And in general, of course, if you want to write down the equations of motion, you would have that theta dot. Sorry, I want to just write down first the Hamiltonian here. That would be p squared over 2m r squared plus whatever potential energy I have. Typically, the potential energy would be minus mgr cosine theta, right? So I can write down the equations of motion. Theta dot would be theta, the Poisson bracket with h. So that's just p over m r squared, whereas p dot would be the Poisson bracket between p and the Hamiltonian. So computing that, I get minus mgr sine theta. That's just computing the Poisson brackets. So with that, I have the time evolution of essentially of any point here. I can write that down. Any questions so far? Okay, so with that, let's that's the structure of the phase space. So the phase space we identify with the cotangent bundle. It's the union essentially of all of the cotangent spaces of all the dual spaces in configuration space. So with that, let's discuss now. We saw, for example, and you know that the equations of motions are described by the Poisson brackets here, right? So essentially, what we have here is the elements of a tangent vector, because it's the time derivative of the coordinates of some curve here in phase space, right? So what's on the right hand side here is some sort of vector, and let's try to figure out what that is. So this means that the structure here of the Poisson bracket should be some vectors, should be related to this vector structure. So let's discuss that. The structure of the Poisson bracket. So in general, the Poisson bracket maps two functions on phase space to a real number. So the way that is done is that you have f and g, and that's by definition That's drf omega rs ds g. And now I'm using these y coordinates, right? I'm using these coordinates where that include all of the these y coordinates that include all of the q's and all of the p's, right? And this omega here, omega rs, that's defined as the Poisson bracket between yr and ys. And you know that you can get this in canonical coordinates. You can get this by inserting the p's and q's here, and you know that it's 0 if both y's are a q, or if both y's are a p. If one y is a q and the other is a p, then you get something general non-zero in canonical coordinates plus minus 1. Okay. So that's that structure. But you can see now that this is, you can recognize this somehow, right? So what we have here is something with upper indices, and we can recognize these things. They are the components of the differentials of f and g. And this is a linear transformation, both in f, in the derivative of f, and in the derivative of g, right? So this omega, it represents some the components of some 2-0 tensor. So a map from differentials to real numbers. So I'm going to call that whatever that the tensor is, I'm going to call it capital omega of the f dg, right? This is defined as the tensor which has these components. And you can easily verify that this indeed transforms in the correct manner to be a 2-0 tensor under coordinate changes. So apart from being linear, we can see that omega here is also antisymmetric. Simply by virtue of the Poisson bracket being antisymmetric. And furthermore, let's check how omega acts on the differentials of the coordinates. So if, for example, if I introduce the coordinate functions here, so I take the qa and the pb, then that's by definition going to be equal to the Poisson bracket between qa and pb, that's delta ab, right? Similarly, if I take omega dqa dqb, that's the Poisson bracket of 2 q's, so it's 0, but that's also equal to the Poisson bracket of 2 p's, so dpa dpb. So that fully defines the this rank 2 tensor. You might now think, we have discussed antisymmetric tensors to quite some extent. We talked about these differential forms, right? This is not a differential form, because differential forms were 0p tensors, and this is a 2-0 tensor. However, we can define a different 2 form. So let's discuss the 2 form. Omega, and I'm now just going to define that as dpa wedge the QA. And I'm going to come to its relation to the capital omega very soon, right? So this means that if I take omega, omega being a two form takes two tangent vectors as its argument. So two tangent vectors on phase space. Well, for example, I can take the QA and the PB, right? Now, by definition, I just insert them here. When I insert this here, I get a 0. Well, let's write this out. So it's an antisymmetric. This is dPA dQA minus dQA dPA. So when I insert the dQA in the first term here, insert it there, I get a 0 because they are independent. When I insert this there, I get a 0 as well. However, when I insert in the second term, this one I get something non-zero, and this one I get something non-zero. So essentially, I get a minus here, delta BA. Just by the definition of this two form. So I'm now going to introduce a little bit of notation. So we let omega of x be the one form. Omega, and we're just leaving that we get by plugging in x into the second argument, right? So if I plug in an x into the second argument here, I still have one argument left, and so I have a linear function from vectors to real numbers. So that's a one form, right? So using that notation, let's check the following. So I had the capital omega. So this antisymmetric 2-0 tensor. It should take two one forms as arguments, right? So if I take the first argument to be the QA, and in the second argument I plug in omega of the QB, which is also one form, then that is equal to omega of the QA dPB, right? Because if I plug in dQB in the second argument here, this is the term that survives, and that has then the dPB. That's what comes out. But we know that this is delta AB, right? And I can do the similar thing here for the P's. dPA, I can plug in omega of the PB, and in the same way, what I get out is delta, in this case, BA, right? So what this means is that omega, and inserting, well, essentially the same thing, inserting the lowercase omega into the second argument, that makes omega the inverse. Is the inverse of the lowercase omega. So I could use the lowercase omega like this to map a vector to a one form, and I can use the capital omega to insert in the second argument. If I insert a dual vector there, I get a vector out. So if I compose those, I map a vector to a vector. And what we see here is essentially that what I get is the identity transformation, which means that the capital omega is the inverse of omega. When you see both as when omega as mapping vectors to one form, and capital omega as mapping one forms to vectors, then the composition of those is the identity. So in general, then, if we write in the general coordinates, we take omega of the r, the s, that's defined as the omega rs, and the capital omega dyr, dys, we define as omega rs with indices, with indices upstairs. Then since the lowercase omega is the inverse of the capital omega and vice versa, we would have something like this, so omega rs, omega st, that would be equal to delta rt. So this is similar to what you have in a Riemannian manifold with the metric, right? Just that omega here is antisymmetric, whereas the metric is symmetric, but it's similar. So in the metric case, we have the metric itself, which maps vectors to dual vectors, and we have the inverse matrix, which goes in the other way. In this case, we have a two-form which maps vectors to dual vectors, and a 2-0 tensor which maps dual vectors to vectors. So it's similar but different, because it's not symmetric. It's antisymmetric. So yeah. So with this formalization now, let's look at what happens to the phase space flow. Generated by some function g on phase space. So in general, of course, if g is the Hamiltonian, then this flow is the Hamiltonian flow, which is the time evolution, right? So if I write this down, y dot r was by definition yr Poisson commutator with g, right? But this, we saw, this was omega of dyr dg. So this is now equivalent with omega rs y dot s. This is just applying omega, lowercase omega, to both sides, being equal to the rg. Or if I want to write this in a coordinate-free form, that the flow here, the gamma, a curve that is following this flow, the tangent vector of that, if I apply omega to it, I get the differential of g. So essentially, if you have this g, then the flow generated by g has a tangent given by the differential of g and the form omega. Right, so if you know g and you know omega, then you can write down the equation of motion for the flow. Okay, so just an observation here now regarding this omega. these two form. The form omega satisfies that omega is equal, well, let me just write down omega, what we had. So omega was defined as the Q, I read the PA, wedge dqa, right? So this means that if I define chi here, xi as a one form, which is PA dqa, then omega is the differential, the exterior derivative of xi, right? Because this is then the PA dqa, so that's just the PA wedge dqa, right? But in addition, this means that omega itself that if I take the exterior derivative of omega, that's the exterior derivative of the xi. But that is zero, because the exterior derivative of any exterior derivative is zero, right? So in particular, I find that the omega is equal to zero. Now I will be using this in a little bit. So we have 8 minutes before the break, so I will use those 8 minutes to just sum up here what is called symplectic geometry. So this is essentially a general form of describing a Hamiltonian system. Without the reference to any Lagrangian mechanics. So mechanics. So no reference to this underlying configuration space M or to tangent bands, just the system itself. It says that a mechanical system is described by its phase space. By a phase space which is a 2n dimensional manifold. So an even dimensional manifold. On this manifold, there exists a non-degenerate antisymmetric follows a non-degenerate 2 form omega, which is then called a symplectic form. With the omega equal to 0, as we saw. So non-degenerate essentially means that it can be inverted, right? And we saw that our omega here could indeed be inverted. And the time evolution then of the system is given by by the flow. So essentially this at omega gamma dot is equal to dH for some Hamiltonian function, right? So I want to note here that in general for a system like this, there's no reference to a metric whatsoever here. I mean, typically in configuration space there is a reference to metric, but there is no need for a metric in a phase space itself. But these requirements essentially summarize everything that there is to know about the system in Hamilton mechanics. So what we just saw is that these things apply essentially to all of the things that happen in Hamilton mechanics. So whatever statements we're going to be able to do about this symplectic geometry is going to apply to any Hamiltonian system as defined previously as well. Any questions on that? Okay. So I think now is actually a good time to take a break. Well, actually, let me do one thing before the break because we have a couple of minutes. So a note about p-forms. So just to prepare for what we will be doing then the next hour. So so if we have given a p-form, let's call it omega for the sake of it. In symplectic geometry, this is going to be the 2 form, but let's work with p-forms in general. We define that if you take omega and you wedge it together n times, this is defined as omega to the power of n. Now, you should note here that if you have two p-forms, have omega is a p-form and psi is a q-form, then if you take the wedge between them, you get -1 to the pq of psi wedge omega. So changing the position, you change the sign if the product of p and q is odd. And you can see this if you essentially write it down, this wedge, right? So let me do that. So this would be equal to 1 over p factorial q factorial, then omega a1 up to ap psi b1 up to bq, and then you would have all of these, the a1 wedge up to dy ap, and then the dy b1 all the way up to dy bq, right? So in order to change the order here between them, I essentially need to get all of the dyb's on the left hand side of all the dy's. So in order to do that, I first need to commute the first one p times, getting p minus signs, and I have to do this for each and every one of the dyb's, which means that I have to do it p times q times, getting p times q minus 1s, which is exactly that, right? So that is true in general, but it means that if you take, for example, omega wedge omega, that's going to be -1 to the p squared omega wedge omega. So if p is odd, this implies that omega wedge omega is equal to 0, but in general, if p is even, is just a statement saying that omega wedge omega is equal to omega wedge omega. So in general, we are not going to run into those problems for even forms, which is what we will be using in the next hour. Okay. So yes, we should be seeing that again. So let's continue where we left off. So I after last lecture I made a short additional recording regarding Liouville's theorem, which is essentially saying that that the phase space volume is preserved under Hamiltonian flows. So flows generated by some function, as we have discussed, right? Now, personally, I always found that to be a very strange statement, right? What is the volume in phase space? I mean, people would typically just, you just multiply the differentials together and you get something nice, right? And you'll see that is preserved under the flow equations, just as I showed in that recording. However, I did not really get it until I studied integration of differential forms and this formulation of symplectic geometry. So if we revisit now Liouville's theorem using differential forms, differential forms using symplectic geometry. So we first need to define what volume means on phase space. So we discussed, when we discussed integration on general manifolds, that that if you want to have the volume of something, you want to have a volume form, then that's a form of the same in n dimension. It's an n form, right? So in phase space we have 2 n dimensions, right? So to make a volume integral, in some sense, we need a 2n form. So we need a 2n form to define volume. What volume even means. And while we discussed that in the Riemann case, when you have a metric, there is a natural volume element. This is no longer the case in a symplectic geometry, right? At least not using a metric. Because we generally have no metric on phase space. So that's kind of what was confusing me. There is no metric, so how can we define volume? Well, we have a symplectic form instead. So we have no metric, but we do have a symplectic form. Omega, which is a 2 form. Yeah, you say, but I need a 2n form. Okay, The natural volume in phase space is given by defining the volume form, the phase space volume form. And let me just see that I call it the same thing. Yeah, I called it eta. So eta equal to omega to the power of n. So as we just saw before the break, this is perfectly fine because omega is a 2 form. It's an even form. If omega had been an odd form, we could not raise it to any powers because we would get 0. So since omega is a 2 form, this is a 2n form. And it is naturally connected to what we had, right? To the symplectic form, to the symplectic geometry. So this defines the phase space volume element, and you can see that since in canonical coordinates, we had that omega was dpa wedge dqa. You'll see that omega to the power of n, that's just the wedge product n times I equal to 1 to n of dpa wedge dqa. So this is going to be essentially dp1 wedge dq1 wedge dp2 wedge dq2 wedge and so on. So this is indeed just containing all of the canonical coordinates once. Okay, that's good. That defines a phase spin volume element. So what remains to show in order to show Liouville's theorem is to show that this is actually preserved, that the volume of some region is preserved under the phase space flow generated by some function. So in order to do that, let's do the following. Let us represent, let G tau represent the Hamiltonian flow in time tau. So for small tau, you would have, if you do this G tau star on omega rs, that would to leading order in tau, it would be equal to omega rs itself plus tau times the lead derivative in the flow direction of omega rs. Right? Okay. So what does that mean? Since the flow is Hamiltonian, is generated by some function h, so the Hamilton function, we know from the equations of motion that omega rs y dot s, actually let me use the same indices as I used in the lecture notes, so I used SR instead. That must be equal to ds of the Hamiltonian, right? So I can use this. I can use this to take a differential here. I can take the differentials on both sides. So with respect to yt. So differentiate with respect to yt, and what we end up with is the following. So we have a chain rule. We have dt dsh on the right hand side, and we have the chain rule on the left hand side. So we get y dot r dt omega sr plus omega sr dt y dot r, right? That's just applying the same differential to both sides. So I'm going to use this to be able to compute the this Lie derivative here. So this implies that if I take this Lie derivative, y dot omega rs, then it's a Lie derivative of a rank 2 tensor. So what I have is first of all y dot t, and then dt omega rs. Okay, but then I have two more terms, one for each free index here. So I have a plus omega let's see, drt, and then ds, and then y dot t, right? Plus omega, and then we get the t here, ts dr y dot t, right? That's just applying the Lie derivative in general to a rank 2 tensor. So what does that mean? Well, I don't really like these derivatives. I would like to rewrite them in terms of the Hamilton field here, and with a derivative that is outside. So to take the y dot outside. So in order to do that, I can apply this relationship, where I have dt y dot r. It's exactly what I have here, and then I have omega ts. Well, it's more or less what I have here. I need to change the indices a bit around, right? But essentially you get the idea for that. So if I do that correctly and keep the indices in mind, I get the y dot t. The first term I will leave unchanged, omega rs. The second term turns into ds dr, acting on the Hamilton function, minus y dot t ds omega rt, plus and then the third term here, using the same kind of expression there and keeping all the indices correctly in mind, is y dot t dr omega omega st minus dr ds acting on h. And you see where this is going now, right? So here those two terms are the same term, just exchanging the derivatives. So we assume that the partial derivatives commute. Sorry, that's not zero, but it cancels that term, right? And then we're left with something that's proportional to y dot t. So let's take the y dot t out and write what's left, dt omega rs. And let me now change the order of the indices here. So plus ds omega tr. That's just changing these indices because omega is antisymmetric, and I get a sign. Plus dr omega st. Now, and you can see that if omega is antisymmetric, which it is, then you can actually rewrite this as y dot t divided by 2, and then the TRS components of d omega. Okay, so that's that. But we saw before, and we required when we defined the symplectic geometry, that omega, the exterior derivative of omega should be equal to 0. So this, given that we have a symplectic geometry, is equal to 0, right? So this in particular means that G star of omega is omega itself. So we have a symmetry, right? In some sense, that this flow preserves omega, which means, of course, that it's going to preserve omega to the n as well. So if we want to write that down, consider now a region P in phase space. So you would have some region P, and then during the time evolution here, that would map to some other region. It can have some distinct shape, but it will be mapped to some other region G tau of P during the Hamilton flow. So what I want to know, or what Liouville's theorem states, is that the volume of this region should be the same as the volume of that region. So let's just check that that makes sense. The phase space volume of G tau of P is defined, let's write this like this. That's by definition equal to the integration over P of the volume form, which we said was omega to the power of n. Right? Sorry, not over P, but over the region. So G tau of P. Okay? But just using the basics here, whatever omega is and whatever G is, this has to be equal to the integral over P of G star tau of omega n. But we know now that that omega was preserved by this flow. So without any further ado, we can write this as the integral over P over omega n, which was just the volume of P itself. Right? So this actually proves. So this is Liouville's theorem, expressed in a symplectic geometry. It should be pointed out also that this is not only true for a 2n dimensional region P. We could choose any other. We could choose any region which has an even dimension, and we could use omega to the, let's say, of dimension 2k. We could choose omega to the 2k as the natural 2k form, and the 2k dimensional volume of the region would still be preserved under Hamiltonian flows. So this is actually even more general than Liouville's theory. But in particular, the volume of any phase-space region under Hamilton flow is indeed preserved, as stated by Liouville's theorem. So that concludes what I wanted to discuss regarding the formalization of Hamilton mechanics and symplectic geometry. So are there any questions regarding that? If not, I want to move on to start introducing field theory. Okay, so let's move on. So field theory. You have probably come across field theory in many respects, like when you have the gravitational field, you have the electromagnetic field, but let's dig into what the field theory kind of represents. So you remember that, like in the gravitational field and in the electromagnetic field, is essentially assigning a value of the field to every point in space, and that kind of gives you the configuration of the field. So, for example, if you have the gravitational field that assigns a gravitational potential to every point in space, the configuration is of the gravitational potential is assigning a potential to every point in space, right? This is somewhat different to what we've been doing when we have been discussing Lagrange mechanics before, like, because we have said that our configuration space should be describable by a finite number of discrete coordinates. This is no longer the case, and this is what sets a field theory apart. So let's just write that down. So so far, what we considered configurations described by some generalized coordinate QA with the index here taking some discrete values in some finite integer set. I mean, I use now the index, the uppercase index, but I could as well have put the index in a parenthesis to show that it's a function of the index. So I could just as well have written QA equal to Q, taking the index A as an argument, right? However, in many applications, such as the gravitational field, such as the electromagnetic field, in many applications, the index set, so the set of possible indices A, is not finite or even discrete. And this is going to be the main difference when we discuss field theories, that we will not generally have a finite discrete set of coordinates that describe our setup. So just as we discussed, or I mentioned the gravitational and the electromagnetic field, I want to take a simpler example, actually. Consider the vibrations of a 1D string, so one-dimensional string. So the vibrations go in one dimension. So what I would have, let's say I have something like this. I have two walls, and in between them I have a string. So here the configuration of this string is not given by a finite number of coordinates, right? Because at every point, if I define the coordinate x like this, at every point x, the position of the string, the displacement of the string from the equilibrium might have a value. So for example, here would be q of x. And giving the configurations of the string means giving a function here, q of x, for x between, well, from 0 to L, right? So in this case, the configuration is a function q of x on the index set, which is now the interval 0 to L, rather than just being a discrete set of integers. So here we say that q of x here is a field. It's a scalar field. It's a single number that depends on position x. Okay, that's the configuration. Then just to take the other example of the electromagnetic field, example 2. So electromagnetism, here the configuration space is the potential fields. So the scalar potential phi of x and the vector potential a of x modulo gauge transformations. But I'll not get into too much detail about that. So these are functions on R3 and generally not indexable by some finite set, right? So this is what we're talking about when we're talking about the field theory. So typically a field theory will be a theory where the index set of configuration space is not finite, and it may very well be continuous, as in these cases. Okay, so what can we do? Well, just as we did in the case of a finite index set, we will consider Lagrangians of the form that L is equal to the integral over k. Well, sorry, k here is I want to define k is the index set, so the set on which the index takes values. The integral over k of some function L that generally depends on q, the configuration, but also on the derivatives of q, and possibly on time, and then differentiating that over some measure on the index set. So dk here would be the some volume element on the index set. So this L is the Lagrangian, and what is inside the the integral here is often called the Lagrange density. Because as you will see, typically like this dk, this index set might be, yeah, it might be this interval. So this L would then just be the amount of Lagrangian per length, or in this case we will have a Lagrangian which is integrated over volume. We have a Lagrange density per volume that integrates to a Lagrangian. We also require that L is a local function. That essentially means that I only have one integral over k here. Whatever I put in here, q is evaluated at each position of the integral. I have no cross terms. I have no cross terms where in the integrand where q at one position appears together as a product with q at a different position. So that's a local theory. Given that the action is defined as usual. So the action is the time integral of the Lagrangian. So if you want to express that in terms of the Lagrange density, it would be the integral over both. Well, we take between sometimes t1 and t2. We would have this, right? Of the Lagrange density, dk, dt. So I can essentially write this as the integral over r cross k here of the Lagrange density, and then I can define some new measure. Let's call it whatever. Let's call it eta, where the eta here is just dk and dt. Okay, so this is essentially as a space-time integral, if you want. So it's an integral, in time as well as in position, for example. So typically, like in this case of the string, it would be an integral over the string as well as an integral in time. That's a space-time integral. So to take that example, actually, let's take the string here. So let's consider the string. So with an external force here now, force f of xt. So I can make the force depend generally on both position and time. So what I would have in this case, let me draw it again. I have my setup here. I have a string, and on this string, I'll define, instead of using q, I'm going to define my function as u of x and t, just as the configuration space variables depend on time. This is the case here as well, right? So this would be the corresponding thing of qa of t. How the configuration depends on time. So this is the displacement of the string from the equilibrium at position x and time t. And in addition, I have some force here acting on the string, this would be f of x and t. Now, if this is the case, this is a force per unit length. If this is the case, then the Lagrange density is going to be L is the density of kinetic energy, which I call T, minus the density of potential energy, which I will call, well, let's call it V. So what we'll need to describe here is the potential energy and the kinetic energy per unit length. So T here, well, if you look at the small part of the string, so small part, the string, this is going from x to x plus dx. The mass here, the m, we write it with the m, it's equal to the length density times the x, right? So the kinetic energy here, that's going to be the m multiplied by how fast this particular piece of string moves, but the speed here is the time derivative of the displacement. So that's going to be ut squared divided by 2. That gives you the amount of kinetic energy per length. So I'll just write this out as rho L ut squared divided by 2 dx. Sorry, I want the Lagrange density. What I've written here is the dx. Okay, so that's that. What about the potential energy? Well, the potential energy will have two contributions. One contribution comes from stretching the string, and the other contribution comes from this external force. And if I do that, what I'll find is a potential energy. I'm not going to go through the details because we only have 5 minutes left. Is going to be one term, which is s divided by 2 times ux squared. So this depends on how long has this part of string been stretched. And well, just to give you an idea, the amount of stretch is 1 plus ux squared, right? Because of Pythagoras theorem. So if this is the x, this is ux dx. And so this length of the string is lengthened by that minus 1. So for small oscillations, that's just approximately ux squared divided by 2. And then the energy due to that is this, right? Sorry, that should be a plus. And then the additional energy due to the force, so that's plus F times the displacement itself. That's the potential due to the force. So that means that, yeah, sorry. Where? Here. Yeah. Okay. So if I want to know how much elastic energy is in this small piece of string, I want to know essentially what the L is here. Let's call this the L prime. So the elastic energy is going to be so elastic energy. Elastic energy, that's going to be given by the tension multiplied, so essentially like So v is going to be dx times, let's look at it like this, right? So it's the, if you stretch a spring by some stretch factor, you essentially get the force in the spring multiplied by the distance that you stretch, right? And this is a string with tension. So the tension might also vary because you're stretching it due to these oscillations, but I'm going to neglect that because I assume that I have small oscillations and that the string therefore maintains more or less the same tension. So the stretch here, it's the force, which is equal to S multiplied by displacement. So the stretch, let's not call it displacement, let's call it the stretch. And the stretch here is this dl prime, so the length of the string segment now minus the rest length of the segment, so that's dx minus dx. Yeah, so yeah, so this is 1 plus ux squared minus 1 dx, right? So that gives you exactly this term once you expand the square root. Yeah, so just to say that then this gives us a Lagrange density, which is rho L ut squared divided by 2 minus, because you take t minus v, right? So minus s ux squared divided by 2 minus f u. And then what you do, of course, is you insert this into the action. So you would define the action. That's the space-time integral of this. So it's the integral in time. So from t1 to t2, for example, and from 0 to L over the string of the Lagrange density. So rho L ut squared divided by 2 minus s ux squared divided by 2 minus fu dx dt. And then in order to find the equations of motion for the string, you apply the Euler, you apply the variational calculus to this. You'll end up with an equation of motion which looks essentially like this: minus c squared uxx equal to f divided by rho L. So this is essentially the sourced wave equation, right? And c here is c squared is the tension divided by the density. So we still use the same framework, right? We still use the action framework. We vary the action, and we get the equations of motion. It's just that when we had a discrete and finite set of index set, then we got just couple differential equations generally. In this case, we have a partial differential equation rather than coupled ordinary differential equations.